This chapter is about clustering, also known as unsupervised learning. So the clustering is also known as unsupervised learning. And in this slide, we're going to see the difference between supervised learning and unsupervised learning. So in supervised learning, every data in supervised learning comes with class value or label like this. For example, suppose we have this image and its class value is cat. And for this image, its class value is dog. So every data has its own class values in supervised learning. On the other hand, in unsupervised learning, every data is unlabeled data, meaning we have input data, okay, like this, but we don't have any class values for this data, okay. We have data only, and it doesn't have any class value or label. So that's the main difference between supervised and unsupervised learning in terms of class values. So in supervised learning, every data has class values, okay, and the main goal of supervised learning is when you have new data, okay, whatever it is, when you have new data, the goal of supervised learning is to predict the class value of this new data. Okay, that is the goal of supervised learning. In unsupervised learning, we do not have class values, okay, and we have input data, and similar data actually forms group or clusters. So the goal of unsupervised learning is to find these groups or clusters automatically, okay? That is the goal of unsupervised learning. So finally, we don't cover this, but I'm going to give you a very short introduction of this. There is another learning called the semi-supervised learning. So actually this learning is combination of supervised learning and unsupervised learning. So the goal of semi-supervised learning is, so in any semi-supervised learning, we have some labeled data and also some unlabeled data. So the goal of semi-supervised learning is how to utilize these unlabeled data, okay, to improve the performance of supervised learning, okay? So we have a lot of unlabeled data, and we have some labeled data. Okay, so goal of semi-supervised learning is how to make use of this unlabeled data in order to improve the performance of supervised learning. Okay, that's the goal of semi-supervised learning. So the definition of cluster is the group of similar data. That's the definition of cluster. So a cluster is a collection of data, okay, which are similar between them, and this is similar to data in other clusters. So suppose we have a cluster like this, and the data within the same cluster are supposed to be similar to each other. And if data are in different cluster, okay, one is here, the other one is here, then these two data are supposed to be different. This is similar, okay? That is the definition of cluster. So similar data forms group or cluster. So the goal of clustering learning, unsupervised learning, is automatic cluster detection. Okay, that is the goal of unsupervised learning. So we find the structure. In this case, structure means cluster. Okay, you find the structure that exists in the data without target variable. So as I said, in clustering, we do not have class labels. So we find the structure, okay, in the data without a class label. That is the goal of clustering. So in clustering, similar data belongs to same cluster. So the next question is then how do we define the similarity between two data? So the first issue in clustering is how do we define its proximity or similarity measure? So we have two options. The first one is similarity measure between two data xi, xj. And another option is to define a distance measure between two data. So xi, sj is a similarity measure between these two data. And this value, similarity measure, should be large if these two data are similar by definition, right? And let's say distance measure d of xi, xj should be small if two data xi, xj are similar. Then by definition of distance, this value should be small. So you can use either a similarity measure or a distance measure in clustering. So either way it's fine, but you have to define, okay, either a similarity measure or a distance measure. So for example here, for these two data are far from each other. So if you use a distance measure, this value should be large. And if you use similarity measure, this value should be small. On the other hand, if in this case these two data are close, similar, so if you use similarity measure, this value should be large. And if you use distance measure, this value should be small. Okay, so you can choose either similarity measure or distance measure. Second issue we have to consider in clustering is, so when you run a clustering algorithm, sometimes the algorithm generates a multiple result of clustering. So for example, in this case, this is one example of clustering, and this one is another example of clustering. Then you have to decide which one is better. So by looking at this, this one looks more natural, looks better than this one, right? So you have to somehow decide, okay, which clustering is better than the other. That's the second issue in a clustering method. So finally, in this lecture, we're going to study three clustering algorithms, including k-means and agglomerative clustering and EM algorithm, which are one of the most very famous algorithms in clustering. So in clustering, I said we can use either a similarity measure or a distance measure. So for now here, we're gonna use distance measure for clustering. So these are some examples of distance measure you can use in clustering. The first one is Euclidean distance. This is very famous. So we have, let's say we have two data, and the length of this straight line is the definition of Euclidean distance. As you can see here, the Euclidean distance is defined as square root of the summation of, this means the case attribute of xi, case kth, case attribute of xi, and this is also case attribute of xj. So this is the definition of Euclidean distance, actually the length of this line. And second, the distance measure is Manhattan distance. And here in Manhattan distance, we assume this data space is divided into a grid form, like Manhattan blocks. So you want to go from here to there, you cannot go straight, okay? You have to go like this, right? So this is the length between these two data is number of blocks you have to travel. So that's the definition of Manhattan distance. So this is definition. So this is absolute value of difference between these two attributes, and its summation is summation Manhattan distance of these two data. This one here is more general case. It's called Minkowski distance, and actually these two Euclidean distance and Manhattan distance is a special case of Minkowski distance. So here, if P is 1, okay, and this becomes Manhattan distance, and if P is 2, this becomes Euclidean distance. So actually these two are a special case of Minkowski distance. So distance measure is important in clustering, and if you are interested in more detail of this distance measure, including Minkowski distance, you can take a look at the instance-based learning, where a lot of distance measure is discussed there. So after the clustering is done, sometimes we need to evaluate the quality of clustering. So we need some numerical measures to do that. So we have actually an external measure and internal measure. So in external measure, actually you need some extra information, most likely class labels. So when you have class labels for some data, then you can use external measures. So in external measure, what we actually do is these class labels are how correctly these class labels are clustered, okay, in the result of clustering. That's what we do in external measure. So again, if you want to use external measure, you need some you need cluster labels for some data. And another one is internal measure. So internal measure, you don't need any extra external information. Okay, you can compute the quality of clustering purely based on the structure of clustering. So in internal measure, there are some options. You can choose a silhouette coefficient or a David Boolean index, etc. So in this lecture, I'm going to introduce a silhouette coefficient in the following slides. So let's talk about internal measures. And actually, most of internal measures depend on two factors. The first one is cluster cohesion, and another one is cluster separation. So in a cluster cohesion, what it means is if data are in the same cluster, then these data should be very similar. They should be very close, very tight. Okay, that's the definition of cluster cohesion. Okay, and in cluster separation, what it means is if data are in different clusters, then these data should be far away from each other, okay, as distant as possible. Okay, that's the cluster separation. So this is the definition of cluster cohesion. Mi is the mean value of cluster I. So for every data x, okay, in cluster I, for every data x, you compute this difference between x and cluster mean, okay, and each square value is added within cluster and for every cluster, okay. So that's definition of cluster cohesion, WSS. And this one here is the definition of cluster separations. And again, Mi is the mean value of cluster I, and M is the global average of clusters. So this computes the difference between cluster average and the global average, and each square value is multiplied by the size of cluster I, and this is added across all clusters. And this is definition of cluster separation BSS. BSS means between cluster sum of square. Okay. So this is the definition of cluster cohesion, and this is definition of cluster separation. Okay, and as I said, most of internal measures depend on these two numbers, these two measures. So it turns out that this cohesion value and this separation value, the addition of these two are constant. Okay, that's one interesting property. So there are many internal measures, but most of internal measures depend on these two measures, and it turns out something like this. So internal measure equals alpha beta is constant. Okay, alpha times separation value divided by cohesion value. Okay, again, separation is this, and the cohesion is this. So almost every internal measure looks something like this. Okay, so actually it makes sense. Okay, so good clustering means high value of cohesion. I'm sorry, a small value of cohesion. Okay, suppose we have clustering and we have very good clustering. That means its cohesion value should be very small. Okay. Cohesion is small means data is gathered very closely nearby the clustering center. And also good clustering means very low value of separation. Okay, so good clustering means small value of cohesion, high value of separation. So internal measure looks something like this, and it makes sense. If separation is high, okay, it increases value of internal measure, and the cohesion is small, okay, also this also increases the value of internal measure. Okay, so again, internal measure mainly depends on two factors: cluster cohesion and separation, and looks something like this. There are many internal measures you can choose from, and you're gonna choose one of them called the silhouette coefficient, and this is quite popular. So in silhouette coefficient, you compute this silhouette coefficient for every data first, and then the final silhouette coefficient is the average value of each silhouette coefficient. So let's take a look. So for every data I, okay, you compute AI and BI. So AI is the mean distance between the data and all other data in the same cluster. So if you look at this picture here, so let's say you pick data X, okay, then AI is you first compute distance for every data within the same cluster. Okay, so in this case, you compute distance between X and all others data here, okay? And the average value of this distance is AI, okay? And we have another term called BI. So BI is the mean distance between a sample, this sample, and all other points in the next nearest cluster. So you have to select next nearest cluster first. So X belongs to this cluster, and then you choose the next nearest cluster. So we have two other clusters, and it looks like this one is the next nearest cluster. So BI is actually you compute distance between X and for every data in this cluster. So okay, you compute distance between X and this, okay, this green line here, and then the average distance of these green lines is B. Okay, so AI is the average distance between this data X and for all other data, and the BI is the average distance between this and for every data in the next nearest cluster. Okay, that's BI. So when you have AI, BI, okay, then the silhouette coefficient of data I is defined as follows. It's BI minus AI, okay, it's divided by maximum between AI and BI. Okay, that's the definition of silhouette coefficient of data I. Okay, so for every data I, you have a silhouette coefficient which looks like this. And it turns out this SI, silhouette coefficient of data I, it turns out to be it's less than or equal to -1 and less than or equal to 1. It ranges between -1 and 1. So if silhouette coefficient is 1, that means this clustering is very good. It's well classified. Okay, it's very good clustering. And on the other hand, if xi is -1 minimum value, it's terribly classified. It's terrible. Clustering is terrible. And if this value is 0, it's somewhere between, okay, indifferent. Okay. So the final silhouette coefficient of this entire clustering is the average value of each silhouette coefficient. Okay, that's the final, the silhouette coefficient of the clustering. That's how the silhouette coefficient works. This one shows some example of using a silhouette coefficient. So let's say we have two cases. So this is the result of clustering, or where number of cluster is 2. We have 2 clusters. And if we compute the silhouette coefficient, in this case, this is a silhouette coefficient for cluster 1, cluster 2, and their numbers are quite good. Their average is 0.77. And now this number of cluster is 4. We have 4 clusters which look like this, and their corresponding silhouette value is actually quite low. Okay, in cluster 3, actually some silhouette numbers are negative. Okay, here there is no negative here. So their average is, in this case, 0.61. Here the average is 0.77. So we can conclude, okay, the clustering here is much better than this one. Okay, as you can see, you can clearly see this clustering is much better than this one. And also you can verify this by using this silhouette coefficient. So finally, we can also use this silhouette coefficient to determine the number of clusters. So in this particular cases, if we choose the number of clusters is 2, its corresponding silhouette coefficient is 0.77. So if you choose number of clusters is 4, it turns out the silhouette coefficient score is 0.61, which is lower than this. So then you can conclude that in this particular case, number of clusters should be 2 instead of 4. Okay, now let's talk about specific clustering algorithms. The first algorithm we're going to study is k-means algorithm. K-means clustering algorithm is actually quite old, but still it is one of the most commonly used clustering algorithm. And the algorithm itself is actually very simple. So if you look at this pseudocode, by the way, the K means the number of clusters, and you have to decide this value K up front. So in the beginning, you randomly initialize K centroid of clusters. So centroid means the center of clusters. So you randomly initialize this centroid of clusters, okay, K centroid. And then for every data, you assign this to the closest centroid. Okay, so for every data, this data belongs to one of the centroid, actually the closest, nearest centroid. And then for each cluster, you recompute the centroid of each cluster. Okay, then you actually repeat because the centroid has moved. For every data, you may reassign this data to other centroid, right? So you reassign this data to other closest centroid, and because of this, you have to recompute the centroid of each cluster. So you repeat these two steps, and you repeat this until there is no change. Okay, so that is a K-means algorithm. It's quite simple, but still quite popular. So this picture shows an example of running a K-means algorithm. So in the beginning, we have three centroid of clusters, okay? And sometimes a centroid is called a seed. So seed 1, seed 2, seed 3. Again, these are randomly initialized, okay? And then for each data, you assign this data to the nearest centroid. So for example, for this data, its nearest centroid is this. So this is assigned to this one, this centroid. So all these are assigned to this cluster, and I think this data are assigned to this centroid, and these are assigned to this centroid. I think for this data, I think this is assigned to this centroid. Okay. So then we recompute the center of this cluster again, because for this cluster, this four data belongs to this centroid, right? So this centroid has moved to the center of this four data, like this, right? By definition, this is center of cluster, okay? And this cluster has four data. So this centroid has to move to center of this four data. Now again, same thing. This data has five data. This cluster has five data, and this is centroid. That means this has to move to center of this five data, somewhere around here. Okay. So this centroid is moved from here to here, okay, which is center of these five data. And finally, this centroid contains this data, and again, it has moved to center of this data, which is somewhere here. So this centroid has moved from here to here, okay? So because this centroid has moved, you have to recompute, okay? You have to recompute the assignment of each data. So for this four, I think there are no change. This four data still belongs to this centroid, and this five still belongs to this centroid, and this data still belongs to this data. But for this data used to belong to this centroid, but right now this centroid has moved to here. So I think this data now belongs to this centroid, right? So there is one change here, okay? So because there is change here, because of this reassignment, you have to recompute each cluster centroid again. So we keep these two steps, and at the end we have one cluster here, and one cluster here, and another cluster here. Okay. So that's the how the k-means algorithm works. This is another example of k-means clustering. So in this case, k equals 2. So we have two initial centroid here. And for this 6 data, these belong to this red centroid. And for this 4, this belongs to this centroid. And then because this is center of cluster, this should move to the center of this 6 data. It's here. And then again, this one should move to the center of this 4. It's somewhere here. Okay. Then recompute, okay, the membership of each data. So for this now, this 5 still belongs to this centroid, and this one used to belong to this one, but now this one is closer to this one, right? So now this belongs to this one, okay? And for this 3, there is no change here. This 3 still belongs to this centroid, but for this, this used to belong to this, but now this is more close to this one, right? So this belongs to this one. So now this one has changed from this to this. And this one also changed from this to this, okay, like this. So you again repeat these steps, okay, until there is no change. So in the pseudocode of K-means algorithm, I said we stop the K-means algorithm when there is no change in data points. So in this slide, actually there are a few more stopping conditions in K-means. The first one is, as we have seen in the pseudocode, you can stop if there is no change in data points. Or the second case is you can stop the algorithm if there is no change in centroid values. And this third one is interesting. You can stop a K-means algorithm when its WSS value is minimum. Okay, if this value doesn't decrease anymore, it is minimum, then you can stop there. So these 2 cases are easy, and this third case is interesting. Okay, the reason for the third case is the following. Actually, this K-means K-means is an optimization problems, and this K-means algorithm is trying to minimize this formula. Okay, that's the goal of K-means algorithm. So when you run K-means and the value of this WSS is minimum, then your goal is achieved. Okay, that's why you can stop there. By the way, I think this formula is familiar to you. This formula is mentioned, studied in cluster evaluation, and this is the measure of cluster cohesion. Okay, so actually what K-means does is K-means is trying to maximize cluster cohesion by minimizing this formula WSS. Okay, that's what K-means is trying to do. Finally, instead of no change of data points or no change of centroid, you can say just a few changes. You can do it. Okay, so far we have seen how this K-means algorithm works. Now take a look at some strengths and weaknesses of K-means. Some strengths of K-means is, first of all, this algorithm is very easy to understand and very simple. Okay, it's very easy to understand and very easy to implement. And this algorithm is fast actually. Its time complexity is O T times K times N. So N is the number of data, and K is number of cluster, and T is number of iterations. And this T and K is relatively small, okay? So that means this time complexity is small. So K-means is relatively a fast algorithm. So since both K and T are small, this algorithm is linear algorithm, very fast algorithm. So in practice, most of the convergence happens in just a few iterations. So if you run this just a few iterations, then the algorithm converges and stops. Even though the k-means algorithm is simple and fast algorithm, it is not actually the most powerful clustering algorithm. It has a bunch of weaknesses. So in k-means, we compute the centroid. The centroid is the mean of each cluster. So we apply this algorithm only if the mean is defined. Okay. So if the data attribute, the value of data attribute is continuous, it's fine. But if attribute value is categorical data, it is not easy to compute the mean of attribute, right? So in that case, you can simply compute the centroid as the most frequent values. Second weakness is the number of k. The user need to decide the number of k, okay, in advance. Okay, that's not easy stuff. And the third one is, as I mentioned in the earlier slide, the k-means algorithm optimizes WSS. Okay, that means it maximizes a cluster cohesion. So sometimes the k-means algorithm ends up in local optimum. Okay, so the answer of k-means it doesn't guarantee a global optimum. The fourth weakness is the algorithm is sensitive to outliers. Okay, and if your data has some outliers, okay, outlier is the data which is very far away from other data points. That's definition of outliers. So if you have a number of outliers, then the result of clustering by k-means is not very good. Okay, so if in many cases outliers are kind of erroneous data, it's error noise data. So if you run k-means, then because of this outlier, okay, then you may have not a very impressive result. Okay. There are some other limitations of running k-means algorithm. So k-means algorithm has some problems when the clusters are different in terms of size and in terms of densities. And if the clusters are not a globular shape, then the k-means has difficulty in finding these clusters. So for example, in this case, let's say we have this original data. Okay, you can clearly see there are 3 clusters here, 1, 2, and 3. But the problem is this one is very big compared to other 2, okay? But if you run a k-means algorithm and you try to find 3 clusters, the natural answer should be this, this, and this, right? But instead, if you run k-means, it's going to find something like this, this, and this. So the reason is, as I said here, k-means has difficulty in finding clusters in different sizes. Okay, so in this case, this one is big and these 2 are small. So in these cases, k-means has problems in finding this. The k-means algorithm also has problems when finding clusters in different densities. So for example, this is original data, and so we have 3 clusters, but these 2 clusters are very dense, and but this cluster is very sparse, right? So they are different in terms of density. So if you run k-means, it's gonna find something like this. Okay, 1, 2, 3. Okay, so the natural answer should be this, this, but the output of k-means looks something like this. Okay, which is no good. Finally, when you run k-means, the clusters, okay, k-means detect is a ball shape, globular shape, okay. So if the shape of a cluster is not ball shape, globular shape, it is very difficult to find it, okay. So for example here, you can see this is one cluster, this is another cluster, but it's not ball shape, okay. So if you run k-means, it's gonna find something like this and this. Okay, so it cannot find the cluster or something like this. So the only cluster the k-means can find is cluster which look like a ball or globular shape. Okay, that's another problem. So we have seen some limitations of k-means. And one way of overcoming this limitation is the following. So suppose here, these clusters are different in terms of size. Okay, this is big and these two are relatively small. Okay, so if you run k-means, it's gonna find it's not going to find a cluster like this. As you can see in previous slide, it's going to be different, right? So to solve the problem, to overcome the problem, the one answer is, one solution is to use many clusters. So instead of 3 clusters, you find 10 clusters. Then it's going to find something like this, okay? Then after this, you merge small clusters step by step, okay? So by doing so, eventually you're gonna find a cluster like this. Okay, so that's one way of overcoming these limitations of k-means. Another issue in k-means algorithm is the result of k-means algorithm is very sensitive to the initial value of centroid. So in this case, the seed means centroid. So for example, let's say we have data. Okay, these two are same data with different initial centroids. So these two are initial centroid here, and here these are two initial centroid. So same data with different centroid values. Okay. So if you run k-means algorithm with this initial centroid, okay, then you're gonna see something like this: iteration 1, iteration 2. But here with the same data with different centroid, you're gonna be something like this at iteration 1 and iteration 2. So it shows completely a different cluster, okay. So it wholly depends on the initial centroid value with the same data. Okay, so that means this k-means algorithm is very sensitive to the initial value of centroid. So to solve the initial centroid problems, people do a couple of things listed here. The first one is you run k-means multiple times with different centroid. Okay, so you run k-means with initial centroid, and then after that you change the value of initial centroid and run again. Okay, so that's the first solution. And then the second one is you try to find more reasonable, more correct initial value. So you cluster your data by using other clustering method like hierarchical clustering. Okay, so by using this, you have more correct guess of initial centroid. Okay, That's our second method. And the third one is you run k-means with more than k centroid, okay? And at the end of algorithm, you're gonna see the final value of k, more than k centroid, okay? So you among them, you choose k of them, okay? So that's the third solution you're gonna try to solve initial centroid problem.